We have spent 2 episodes circling one number without ever pinning it down. We said an 8GB laptop runs the small models, 16GB the mid ones, 32 and up the big ones. But where do those numbers come from? Why 8 and not 5? Why is a 70 billion parameter model out of reach for most laptops even after we shrink it? Today we make it exact. By the end of this episode, you will be able to look at any model and any computer and know with a quick bit of mental math whether it will run, whether it will run well, or whether it will crawl. And it all comes down to one resource that matters more than processor speed, more than brand, more than almost anything else: memory. Specifically, the fast memory called VRAM and its clever cousin, unified memory. Quick note before we dig in. If you find this useful, subscribe and drop a topic you want explained in the comments. Now, let us get into it. First, why memory and not speed? Go back to episode 6, to attention, where we said the transformer does an enormous number of calculations all at once, in parallel. That is the key. Running a model is fundamentally a tidal wave of parallel math, multiplying huge grids of numbers. A regular processor, a CPU, does a few things at a time, very fast, one after another. A graphics chip, a GPU, does thousands of simple things simultaneously, which is exactly the shape of the work a model needs. Graphics chips were built to color millions of pixels at once for video games, and it turned out that same talent is perfect for running AI. But there is a catch, and it is the whole episode. To do that math fast, the chip needs the model's weights sitting right next to it in its own dedicated ultra-fast memory. That memory is called VRAM, Video Random Access Memory. And the iron rule is this: the entire model has to fit inside that fast memory at once, or things fall apart. So here is the whole idea in one sentence. To run a model quickly, all of its weights have to fit in your fast memory at the same time, so the amount of memory you have, not the speed of your chip, is what decides which models you can run. If a model fits in your VRAM, the graphics chip rips through it and you get fast, smooth answers. If the model is even a little too big, it cannot all sit in that fast memory, so part of it has to spill over into your regular, much slower system memory, and the chip is left waiting around for data. The result is not a small slowdown. It is often a tenfold or worse collapse in speed, a model that types one painful word every few seconds. There is no graceful middle. It fits and it flies, or it does not fit and it crawls. That cliff is why memory is the number that matters. Now the part that makes you dangerous, the actual arithmetic. And it is easy. Remember from the quantization episode that a weight is a number, and its size depends on how precisely it is stored. At full 16-bit precision, each weight takes 2 bytes, so a model needs about 2 gigabytes of memory for every billion parameters. A 7 billion parameter model at full precision then needs roughly 14 gigabytes. But you are almost never running full precision locally because, from last episode, you quantize. At 4-bit, each weight shrinks to about half a byte, so the rule of thumb becomes roughly half a gigabyte of memory per billion parameters, a touch more in practice once you account for the format's overhead. So, here are the numbers worth memorizing, all at the 4-bit setting you would actually use. A 7 billion parameter model needs about 5 gigabytes. A 13 to 14 billion model about 9. A 30 billion class model around 20. And a 70 billion model, roughly 40 gigabytes. Now, those 8, 16, and 32 gigabyte thresholds from earlier make perfect sense. They are simply the memory it takes to hold the model after quantization. There is one more thing you must add on top of the weights, and it ties straight back to episode 4. The context window is not free. As the model reads your prompt and holds the conversation in mind, it stores a running set of intermediate values for every token in the window in something called the KV cache. That cache lives in the same precious memory, and it grows as your context grows. So a longer conversation or a bigger document does not just cost you tokens from episode 2, it costs you memory right now on your machine. The practical move is to budget roughly 10 to 20% extra memory on top of the model's weight size to leave room for context. So that 70 billion model that needs 40 gigabytes for its weights really wants closer to 45 or 50 once you give it room to think. Bigger window, more memory. The context window and your VRAM are connected at the hip. Now, why do Mac owners keep showing up in these conversations punching above their weight? Because of a genuinely different design called unified memory. On a typical gaming or workstation setup, the graphics card has its own separate pool of VRAM, often 8, 16, or 24 gigabytes, walled off from the computer's main system memory. That dedicated VRAM is what your model has to fit into, and on consumer cards it is often the bottleneck. Apple Silicon Macs, the M-series chips, do it differently. The processor and the graphics chip share one single pool of memory, the machine's whole memory, with no wall between them. So if you buy a Mac with 64 gigabytes of unified memory, a huge slice of that is available to hold a model, far more than a typical graphics card offers. This is why a well-spec'd Mac can quietly run a 70 billion parameter model that would need 2 expensive graphics cards on a traditional setup. One practical note, the tool does not hand the model every last byte. Allama, for instance, reserves a chunk for the rest of the system and treats only around 70% of your unified memory as the budget for the model. So that 64 gigabyte Mac effectively offers somewhere around 45 gigabytes for AI, which, look back, is just enough for a quantized 70 billion model with room for its context. The numbers all connect. So how does this land depending on who you are? As an individual, this is your buying guide and your reality check, and the tiers are clean. 8 gigabytes of memory comfortably runs the 8 billion parameter class, plenty for everyday assistance. Around 24 gigabytes, whether a dedicated card or unified, opens up the genuinely strong 30 billion class, the current sweet spot for serious local work. And 48 to 64 gigabytes of unified memory on a high-end Mac brings the 70 billion models near the top of what is possible at home within reach. Match the model to the memory and you are set. As a startup, this exact arithmetic is your cloud bill. Renting a machine with more high-speed memory costs dramatically more per hour, so quantizing a model to fit on a smaller, cheaper instance, or picking a model whose memory footprint matches affordable hardware, is one of the biggest levers you have on the cost of serving AI. And as a large enterprise, this is capacity planning at scale. The amount of high-speed memory across your servers sets a hard limit on how many models, how large, and how many simultaneous users you can serve. So memory, not processor count, is usually the constraint your infrastructure team is actually managing. So let us bring it home. Running the model fast means fitting all of its weights into fast memory at once, so memory, not speed, is the number that decides what you can run. At full precision, reckon 2 gigabytes per billion parameters. At 4-bit, roughly half that, then add 10 to 20% for the context window's KV cache. VRAM is the dedicated memory on a graphics card. Unified memory is Apple's shared pool that lets a Mac hold unusually large models, and the clean tiers are 8 gigabytes for 8 billion, 24 for 30 billion, and 64 for 70 billion. That closes out the foundations. Over 9 episodes, we have built the whole machine from the ground up, what a model is, how it reads in tokens, turns them into meaning, holds a limited window, samples its output, focuses with attention, and how you run one yourself on real hardware. Now, the series turns from how the machine works to how you actually wield it. Because owning a powerful model is one thing, and getting it to do exactly what you want is another skill entirely. In the next episode, we begin part 2 with the craft that more than anything separates good results from frustrating ones. Prompt engineering that actually works, that is the core of it. If this helped, hit like and subscribe, ring the bell for the next deep dive, and tell me in the comments what you want broken down next. Thanks for watching.